Hello everyone, this is Shankar Rai Kormokar and welcome to my channel that is Reverberation Guidelines. Today we are going to discuss about the several type motions of an object. If we highlight the types of motion of an object, then we will find that the motion can be classified into two parts. One, static motion, and number two, the dynamic motion. The dynamic motion can further be classified into two more parts, one kinematics and number two kinetics. So if we highlight on kinematics, we will find that this is the branch of classical mechanics which deals with the motion of an object without considering the cause of the motion, that is the force or the torque applied on the object. But the kinetics is the branch of physics or engineering that deals with the classical mechanics, which has the relationship between the motion and the cause of the motion.
Now, before we start the chapter, we would like to tell something about reference frame. A reference frame is nothing but a Newtonian frame, which is the abstract coordinate or a system which detects the motion of other objects. Basically, with respect to time, the reference frame does not change its position and it is always fixed. If an object does not change its position with respect to time with respect to the reference frame, then we can term the motion of the object as static. But if the object starts changing its position with respect to time with respect to the referential frame, then we will term the motion as dynamic motion. The railway stations, the buildings, the apartments are the examples of several referential frame, and it does not change its position with respect to time. Now, if we try to classify the kinematics, then we can find there are three major parts: the translational motion, the rotational motion, and the mixed motion. The translational motion is going to be classified into two more parts, one rectilinear motion and number two the curvilinear motion. The rotational motions is going to be classified into two more parts, one circular motion and number two the spinning motion. If we try to describe the translational motion, then all the particles of an object move parallel to each other and they may follow the straight path or the bent path. Now, if we classify the translational motion, we will find two major parts, one rectilinear motion and number two curvilinear motion. Rectilinear motion is also known as the straight line motion, and here the object propagates in a straight path. As a result, it experiences a linear pathway movement. But for the curvilinear motion, the motion of the object may follow two or three dimensions. As a result, this is more complex than the rectilinear motion. Now, to define the rotational motion, we will find that here is a fixed axis or a fixed point. Centering the fixed axis or the fixed point, the object rotates in a circular path, and such type of motion is known as the rotational motion. The rotational motion can be furthermore classified into two more parts, one circular motion and number two spinning motion. The circular motion, which follows the circumference of a circle or rotates along a circular path, is known as the circular motion. The motion of a fan is the example of a circular motion. The motion of a planet is another example of circular motion. Such type of motion may be uniform, may not be uniform, but it always rotates in a circular path centering another object or a fixed point. But for the spinning motion, we know that it rotates around a center or a fixed point or a rotational axis. If we try to observe the motion of a top, then we can easily realize the spinning motion. We know our earth rotates in a circular path centering the sun, and the circular motion across sun is the main reason for the introduction of years. But we also know that the earth rotates around its axis, and such type of motion, that is nothing but spinning motion, is the main reason for the introduction of day and night. We will only concentrate on the translational motion in this chapter, and as a result we will first define the term that is known as distance. So distance is the scalar quantity that refers the path traveled by an object to reach the final destination from its initial point. Now imagine 2 points on screen, that is A and B. So to move at B from A, we can follow the first pathway or we can follow the second pathway. In such way, we can prefer any one of the pathways to reach at B from A, and each and every cases the pathway may be same, may not be same, but the path traveled during every journey is known as the total distance covered by the object on that particular journey. But in kinematics, the displacement is the vector quantity which denotes the shortest distance from the initial to the final position of the object. The object may follow any pathways to move at B from A, but the linear pathway that joins the A and B in a straight line is known as the displacement. And remember, in every cases, the displacement between 2 points will always be same. We are now trying to define the speed. So speed is nothing but the rate of change in distance or the rate of crossed path. It has the unit of meter per second and it is a scalar quantity. Because the distance has no direction, so it has no direction. The rate of change in displacement is known as velocity, and it has the unit of meter per second. As the displacement has the direction, so velocity has also a direction, and as a result it is a vector quantity. The instantaneous velocity is given as v equal to ds dt. That is, for a instantaneous moment, the rate of change in displacement is known as the instantaneous velocity.
In kinematics, the rate of change in velocity is known as acceleration. It is a vector quantity. It has the unit of meter per second square. The acceleration is expressed as a equal to dv dt, that is the rate of change in velocity, and we know v equal to ds dt. So in second order derivative form we can write acceleration equal to d2s dt2. In kinematics, the acceleration is responsible for the change in velocity, and that's why we will try to define several equations based on velocity, time, and displacement. Now, to establish different relations on velocity, displacement, and time in rectilinear motion, we will follow three different pathways. Number one, the algebraic formula. Number two, the graphical representations. And number three, the calculus. So in the section, we will discuss the algebraic formulas as well as the graphical representations to establish several equations. Let us imagine that the initial velocity of the object be u and the final velocity be v, while the object is moving at a constant acceleration of a and it travels for next t second. So the change in velocity equal to the final velocity minus the initial velocity, that is v minus u, and the rate of change in velocity equal to v minus u by t. But we know that the rate of change in velocity is nothing but the acceleration. So a equal to v minus u by t. So simplifying the total factor, we get that v minus u equal to at or v equal to u plus at. And this is the most important formula which we are going to apply in every cases for the next proofs. We have decided earlier that the initial velocity of the object is going to be considered as u, as it is moving at a constant acceleration of a, the final velocity after t time becomes v. So the average velocity throughout the journey becomes initial velocity plus final velocity by 2, that is u plus v by 2. So in next t seconds, the total path traveled by the body is equal to average velocity into time. So a is equal to v plus u by 2 into t. But we know that v equal to u plus at. So finding t equal to v minus u by a, we are replacing the total value of t in that equation. We get 2s equal to v plus u into v minus u by a. So simplifying the total factor, we get v squared minus u squared equal to 2as. So v squared equal to u squared plus 2as. We have decided earlier that the initial velocity of the object be u, and it is moving at a constant acceleration of a. After t second, let the velocity of the object becomes v. So the average velocity throughout the journey equal to initial velocity plus final velocity by 2, that is v plus u by 2. So in next t seconds, the path traveled by the object is equal to the average velocity into time. So a is equal to v plus u by 2 into t. But we know the rate of change in velocity equal to acceleration. That means v equal to u plus at. Replacing the value of v in the next equation, we can get is equal to u plus at plus u whole bracket into t by 2. So a is equal to ut plus half at squared. We are now interested to find the total pathway traveled by the object at tth second. That means the total pathway traveled in t second minus the total pathway traveled in t minus 1 second. That will define as the total path traveled by the object in tth second. So to solve the equation, we will take the help of the previous proofs. We know in t second the total pathway traveled by it is 1 u into t plus half at squared, and in t minus 1 second the total pathway traveled by it is u into t minus 1 plus half into a t minus 1 whole square, and the total pathway is going to be shown by s2. So at tth second, the total pathway traveled by it, that is st, equal to s1 minus s2, and after simplifying the total data, we can find that st equal to u plus a by 2 into 2t minus 1, and this is the total pathway traveled by the object at tth second. In this section of the video, we will try to establish all the equations of rectilinear motion with the help of graphs, and to establish the total scenario, we will consider two axes, one x-axis and another y-axis. In the x-axis, the time is going to be represented, and in the y-axis, the velocity will be represented. We have decided earlier that the velocity will be defined by y-axis and the time will be defined by x-axis. The initial velocity let be ad equal to u, and as it is moving at a constant acceleration, so after t time the velocity will be let be de equal to v, and the time of journey is ab equal to t. So we are now thinking for a point of c in such way that dc is perpendicular over be. As a result, we can say that ABCD is a rectangle. We know the opposite sides of a rectangle are equal and parallel. So we can write AB equal to CT equal to the time of journey, that is nothing but the time t, and AD equal to BC is nothing but the initial velocity, that is u. As a result, now we are finding a triangle, that is CDE. And from the diagram, it is evident that it is the right angle triangle where the side CD equal to the time t and
the side CE is nothing but the BE minus BC, that is V minus U. So if the triangle has the slope of theta, we know tan theta equal to the height by base, that is tan theta equal to CE by CD. But from the velocity time graph, we can write that the slope of the triangle is nothing but the acceleration. So we can write acceleration A equal to CE by CD. But we know CE equal to V minus U and CD equal to T. By implementing the value, we can write A equal to V minus U by T. So simplifying the total data, we can write V minus U equal to AT. So V equal to U plus AT. And this is the most important proof. During the implementation of the rectilinear motion equations, we need to know that the area of the velocity time graph represents the displacement. Now, the displacement of the object is nothing but the area of ABED trapezium, and this trapezium ABED is going to be classified into two parts where ABCD is the rectangle and CDE is the right angle triangle. We know the area of a rectangle equal to base into height and the area of a triangle equal to half into base into height. So we can write is equal to AB into AD plus half into CD into CE. Now implementing the values of AB equal to T, AD equal to U, CD equal to T and CE equal to V minus U, we can write is equal to UT plus half into T into V minus U. But we know V equal to U plus AT from the first equation. So V minus U equal to AT. Replacing the value of V minus U as AT, we can write is equal to UT plus half AT squared. And this is the second establishment of the equation. Now to establish the next equation, we will apply the previous formula. The area of the velocity time graph represents the displacement of the object when the object is moving at constant acceleration. So the displacement of the object S can be given as the area of the trapezium ABED. So we know the area of a trapezium is nothing but the half into sum of parallel sides into height. So in the ABED trapezium, the parallel sides are AD parallel BE. We can write is equal to half into AD plus BE into AB. Now AD equal to U, BE equal to V and AB equal to T. So replacing the values of AD, BE and AB, we can write is equal to half of V plus U into T. But we know V equal to U plus AT. So AT equal to V minus U. So T equal to V minus U by A. So we can write is equal to half into V plus U into T or is equal to half into V plus U into V minus U by A. So simplifying the total factor, we can write V square equal to U square plus 2AS. Now we are considering the initial velocity of an object that is going to be defined by AD equal to U. It is moving at a constant acceleration of A and the final velocity after t second let be V, that is equal to BE. Now the time of journey AB equal to T, but we are interested to find the total pathway at tth second. So we are thinking AY equal to T minus 1 second, that means YB equal to 1 second. Now we are interested to find the pathway traveled by the object in YB second, that is in tth second, and to find the total pathway traveled in that particular second we need to find out the area of YBEF trapezium. We know AD parallel to YX parallel to BC or AD parallel to YF parallel to BE and AB parallel to DC. Again, AD equal to BC equal to U and AB equal to CD equal to T and AY equal to DX equal to T minus 1 second. So to find the displacement at Tth second, we need to find out the area of YBEF trapezium. So to find the total area of the trapezium, we are interested to find the total area of ABED minus the area of the trapezium AYFD. So we can write ST equal to area of trapezium ABED minus area of trapezium AYFD, that is ST equal to half into AD plus BE into AB plus half into AD into YF into AY. But from the trapezium AYFD, we will find that the journey has been traveled by the object for t minus 1 second. So YF will be the final velocity after t minus 1 second, and we know the final velocity can be defined as u plus a into t minus 1, and the final velocity after t second, that is BE, that can be written as u plus at. Implementing the values of yf equal to u plus a into t minus 1 and be equal to u plus a into t, we can write that st equal to u plus a by 2 into 2t minus 1. Thanks for supporting me. Thanks for watching. Stay home, stay safe. See you in next video.